So today I'll be showing how to make an Nmos transistor. This is the type of transistor that turns on when you apply a gate voltage. So we start with the P-type wafer with the 100 crystal orientation. You put it into your kiln or your furnace, and you pump steam into the furnace, and you're going to grow a thick oxide layer that is 5,000 to 6,000 angstroms thick on the top of the wafer. You can tell when you've reached that thickness by a color chart. You can find this color chart online in multiple places. But you're going to be shooting for a green color, and it's going to take about 6 hours to grow that on top of the wafer. The next thing you're going to do is you're going to etch the active layer. So you're going to use the hydrofluoric acid, and you're going to use a vinyl sticker mask that you can cut out. This is like the vinyl signs that you can put on the side of your car. So this is going to mask the oxide from the acid, and you're going to open up active areas into the wafer. You're going to make structures that look like this. It takes about 15 minutes for the Wink rust and stain remover to etch through 5,000 angstroms of silicon. And you can tell when you've etched all the way through is the water will not stick to bare silicon, so it will bead up on the bare silicon, whereas it sticks and wets the oxide layers. So this is the source and drain region that is the active area. So we're going to cut two squares. We're going to try to get in as close as we can to make a channel. The next step is we're going to spin the phosphosilicate film onto the wafer. It's a very thin fluid. You can spin it onto the wafer by using a CPU fan that has double stick tape on it, and you can stick the wafer piece onto the fan and apply this liquid. I found that if you're using square pieces of wafer, that it's better to rock the wafer around and coat it, kind of a thick coating all around first, and then turn the power on and spin it, and then the layer will be, it'll spin off the excess and make a very thin layer. Then you'll put it in your kiln at 1,000 degrees Celsius for 5 minutes for what's called a pre-deposition. The pre-deposition puts a very high concentration of phosphorus into the surface of the wafer. Then you'll take the wafer out of the furnace, let it cool down, and you'll take it out of the furnace, you'll let it cool down, and you'll put it back into the acid, and you'll etch away this film that was left behind. And again, you'll know that you've etched all the way through when the water starts beating up in the active areas again and doesn't wet across. The next step you're going to do is the intermediate oxide layer and the drive-in. So you're going to put it back into the furnace. 15 minutes of pumping steam into the furnace. It'll grow an oxide layer to cover up the source and drain regions. And then you're going to stop the steam, and for 25 minutes you're going to drive the phosphorus into the wafer. This will lower the resistance in this area and form PN junctions between here and here, and here and here. The next step is to etch the gate oxide area. So you'll again use the vinyl masks, and you'll open up where the gate region will be. You'll etch this away, wait for it to be hydrophobic again, and you'll put it into the furnace at 1,000 degrees without steam. And this will vary depending on how much humidity you have in your lab at the time, or your house, or your kitchen. And you'll grow a thin layer across. So shooting for 800 to 1,000 angstroms, if you look at the chart, color chart again, it will be between a kind of dark red and pink color. And you'll have to pull it out of the furnace repeatedly and check. You'll see the tan color come in at 500 angstroms, and then it'll start turning red, and you'll shoot for pink. I've had successful devices that were this royal blue color, which is 1,200 angstroms. This is probably the most difficult part, is gauging the gate oxide. And now for the last step is the contacts, to make contact to the various parts of the transistor. What I use is conductive epoxy. It's a two-part epoxy. This particular type is from MG Chemicals. And your side view will look like this. You'll put a blob of, you'll make another mask. You'll cut through the oxide that's grown. You'll make access points down to the source and the drain, and you'll leave the gate oxide alone. And then you'll put blobs of epoxy to make contact to these areas. And then you'll cover the gate region with epoxy. What happens when you apply a field to the gate, electrons will jump across the channel and will turn this transistor on. You'll also need to make a substrate contact. It can either be on the back side, or you can etch another hole down through the field oxide to gain access to the substrate. This gets rid of the parasitic PN junction in here and makes it act like a transistor. And you hook the substrate up to the source. The source would hook to the ground of your circuit, and you would have your load on the drain side hooked up to VCC. And then by applying a field to the gate, it would modulate the voltage that can flow through. When you're done, your transistors will look like this. This is 5 transistors that I put together for Maker Faire. If we zoom in close, you can see I made a substrate contact along the entire edge. So I etched through the oxide, put a big blob of epoxy there. Down the middle is this royal blue colored gate oxide. You can see how I cut all the transistors at once. And we have source and drain contacts, source and drain, and then gate. So a little later tonight, for you guys that hang out, I'm going to film a little video of hooking this up to the lab power supply. We can turn an LED on and off with it.